Good afternoon, everybody. Sorry, I'm last minute. I got stuck in traffic on the way home from campus, and then I quickly had to set up the computer, and so she got it just before 5, but just. All right, let's give it a few more minutes and see who else shows up. Okay. Yes, Maddie, that is precisely what I'm faffing about with at the moment. Just finding it to get it in there, and then it told me it was open, and then I went, oh yes, because I was adjusting it earlier. There we go. Okay, can everyone see that document in the chat there? Good, thank you. Comforting nods, that's a good thing. All righty, so I think we might make a start because it is 5 o'clock. The good news is that we're topic 8 today, but obviously this week's lectures is topic 9, and you've only got 10. So there's light at the end of the tunnel. You can actually see the end of BMS165. And then that's great. Yay. And then you have to jump into 175. So light at the end of the tunnel and then another tunnel. Yay. But that's fine. That's the way trains work, right? It's fine. We're prepared to deal with this. Okay. So we're reviewing last week's work, and it's fairly important, guys, that you are really on top of this stuff, because if you're not on top of systemic and sort of pulmonary circulation as a broad thing, this week's stuff is going to be a little bit this week's lecture stuff we haven't covered yet in the tute, will be a bit challenging. So just make sure that you're really, really clear on the broad over spectrum of this kind of thing, so that when we get into the details, you're not completely lost. Now, what did I just miss in chat? Someone being terrified? You know, I shouldn't laugh at you, Caitlin, but it's normal to be terrified of exams. Please don't be terrified. Please just take into account the usual thing, and remembering what kind of exam it is. As long as you've written out all the learning objectives and you've got a good, sentence/paragraph for every single one of them, there won't be anything in your exam that isn't directly from the learning objectives. Like that's the rules. That's a promise. So it's just a matter of doing that and conscientiously doing it all the time, and making sure that you've got that little document, whatever it happens to be, digital or otherwise, ready to go, right? With maybe sticky notes for each different topic, so you can flip through it really easily and navigate your way through it. And that's the only trick. So remember, we're not really asking you to digest and memorize everything. It's really a matter of having your notes in order, ready to go. Is it not, people? Is that the plan? Can I repost the worksheet, Emma? I can. Yep. Let me just do that. Okay. Sorry, I stop talking when I'm doing computer things because my brain won't do things, won't multitask on that one. Okay. In any case, shall we jump in and see where our knowledge is? I think that's probably a good idea. All righty. Let's jump. Okay, so like I was saying, I say every week because I like to be a broken record. It's fun. Do your learning objectives and make sure that you've got them all sorted. And here they all are. Your 3 layers of the heart walls, your major vessels, your electrical systems, sinoatrial nodes, etc. The definitions of stroke rate and volume, all of those are really, really important, guaranteed they're going to ask. And making sure you really do understand this whole, how does it work from the major arteries and the major veins down the endless branches to the various capillaries and the capillary beds, and what goes on in the capillary beds. Hint, the big word is exchange of nutrients and or gases, depending on where they happen to be. So these are very, very important things to understand. But, you know, have a look at them, make sure you can describe them, and then you'll be fine. Okay, let's jump in. Now, I've been very nice. I've got all sorts of little circles and shapes and things, and often answers here to help you out. So, which label gives me the sinoatrial node in the broad structure of the heart there? A. Yes, broad chorus of A's. Much agreement across the cohort? Yes, because what would B be?
The AV node.
Yes, absolutely. Sinoatrial up the top of the atrium, AV between the atrium and ventricle. So that's just geography. That question. Good. Are we all happy with that? Did everyone else get, people that don't talk very much, did you get that as well? Do you want to nod at me? Okay. All right. Now, pretty important. And there's a hinty picture up there. Which of these terms means contraction of the heart?
C.
Did you say B?
C.
Oh, C?
C.
I think it could be C, yeah. Now, I'm going to give you my memory thing for this, for the whole systole and diastole. Systole sounds like fist. I know it doesn't, but it does, sort of, right? And in order to make a fist, you have to contract your hand, right? Diastole is relaxation, and because you're dying, right? So you died. So that's when you die, you relax quite a lot. Yes? That's my thing. Cyst, fist, contract. Die. Okay, that's the way I do it. Up to you. You might have a better brain than mine. Okay, good. Next, length of our cardiac cycle. This is one of those remember the numbers, and it's not particularly logical, but what do we think?
C.
I got a chorus of C's. Did I hear a D in there somewhere? It's okay. If you said D, you can pretend you didn't because it is C. 0.8 seconds. Good. And then there's a question here about the difference between our veins and arteries. Big, big, big difference. They've all got the same tunica, right? Intima, media, etc. But veins have this one thing that arteries do not have, which is
Valves.
Valves. And what happens when our valves get stuffed in our arteries? Particularly, hate to say it, women of a delicate age, like myself. What happens to the veins in our legs in particular? Anyone know? Anyone ever seen Auntie Marge with the varicose veins?
Yeah, varicose veins.
Yeah. This is literally valve failure. Okay, so the whole point of the valves is that when your skeletal muscles contract and you've got the various pressure differences and it's pushing the blood back up towards the heart, the valve is supposed to close. So the blood doesn't come back down the other way with gravity, right? But as one gets older, one's valves get older, and sometimes one's valves don't close and then you get this pooling of blood in the vessel just from gravity, and that is varicose veins. So I'm not even going to ask for a hands up of who's got them. I don't, because but honestly, that's not a boast. It's mostly genetic, guys, whether your valves are going to last out or not. So look at your mum in a swimmers next time you see her, and if she's got them, chances are pretty high one day it might be you too. However, this is not a great problem. It very rarely becomes pathological. It just becomes unsightly. So it's just a thing to be aware of. But that happens a lot with aging, right, girls? Unsightliness where there wasn't before. Yeah. Who's got kids? Yeah. What's with the mummy pooch, right? What is that about? Where is that coming from? Why doesn't it go away? Right?
So unfair.
It's not right, is it? I had this beautiful flat belly and it just went away. Not good. Right? And then you do everything in the world, you buy everything you possibly can, you exercise like a demon. Does it go away? No, because that's life. Totally unfair. Anywho, moving along. The friction that blood encounters as it moves and flows through our vessels is called, big bloody hint on the slide. Could be stroke volume. No. Could be the friction. What's another word for friction? Or a simile? What's the only word on there that actually works for that?
Resistance.
Resistance. Yes, absolutely. Peripheral resistance. What stops the flow of the blood through the vessels? What are some examples of peripheral resistance that you can read off the slide? Literally. Is a long vessel more resistant or a short vessel?
Long.
Long. What else can I have? I can have vasoconstriction causing resistance. I can have really thick blood causing resistance of its own. If I have really thick blood, this is kind of revisiting last week. What part of my blood is it that is thick exactly? What's going on with that? When you have thick blood, right? So when your blood is too thick and it's causing this peripheral resistance, or it's part of it, what component of my blood do I have too much of?
Is it red blood cells or?
It is indeed.
It is?
Absolutely. Yep, it is indeed. Yep.
Okay.
So too many red blood cells, generally caused by something stupid like climbing a mountain and needing more oxygen. So you're literally, all of your chemoreceptors in the heart are saying we've got low oxygen. Oh boy, we have the kidneys pumping out EPO and the liver pumping out EPO, goes down to the blood vessel, to the bone marrow, pumps out a whole heap of extra red blood cells because that's the only way we have to get more oxygen. Right. Same thing happens with heavy smokers. Right. Again, chemoreceptors saying we don't have enough oxygen, pump out more red blood cells. So you end up with thick, sticky, viscous, resistant blood. Not a good thing in general. Okay. All right. And although you can take half an aspirin, and that tends to work out quite well. All right. Now, a list of the short and long-term regulators of blood pressure. I'll give you a couple of seconds to have a think about what's a short-term regulator. Hint, we just spoke about one of them. And what's a long-term regulator of blood pressure? And again, because it's tutorial, you don't have to answer the entire question right now. Hopefully you just get to look at your lovely list of learning objectives that you've already answered and you kind of read them out, or you read part of them out to me. That'd be good. And don't forget, if you pick the easy one and you're the first person to talk, then you don't have to talk again and someone else has to do the hard bits. So that's how it works.
Barrow reflex.
Barrow reflex. Good. Is that short or long term?
Oh, sorry, short.
Yep, absolutely. Good. Baroreflex. Now, because you answered, Amy, you don't even have to give me the details about a baroreflex, but what can someone else give me a broad overview of the baroreflex? What on earth is Amy talking about? So we know it's short term because it's got the word reflex in it for starters, right? So if anything that's a reflex is immediate, it's definitely not long term. Baro meaning, what's the definition of baro in physiology? When we see that prefix, what do we know it's talking about?
It's to do with stretching, isn't it?
Yep. And pressure, like a barometer. Yeah, like barometric pressure in the atmosphere. Yeah. So that baroreceptors is all about a pressure and a stretch reflex. Yep. Good. What about long term? So baroreflex is one of them. There's a couple of others for short-term blood pressure maintenance or regulators. Or if we can't get more short terms, how about we jump to what's a long-term regulator of blood pressure? Big one that's complicated, involves lots of systems.
The RAS one?
Yep.
I can't say
RAS. Yes, you can. Renin. What?
And I can't say that.
And you could say it. Renin, angiotensin, and there's another one. Go on, Di. You want to. I can see your mouth trying to do it. You should try it.
I'm trying to remember how Nat said it. Aldosterone, something.
Close enough. Yes, aldosterone. Yep,
Can you
absolutely.
spell it out?
Spell it as right.
While I'm
okay.
trying to type it.
You're writing, and that's fine. So it doesn't matter. You don't have to actually do this as an oral exam.
There's a lot of letters in those words.
You know what? And that's one of the things that people find most, I think, when they're studying medical sciences. It's not actually the concepts, it's the words around the concepts, like the whatty now. Why does everything have to be in Latin? Why? Okay, let's put them out of their misery and going to have a look at these short and long-term regulators, just in case you haven't got this answered in your own learning objectives listy thing. So we talked about the baroreceptor. Yeah, so that's talking about receptors in the aorta that actually detect changes in pressure. Yeah, like barometers. We've got chemoreceptors, reflex. Okay, so what does a chemoreceptor detect changes in? Think about it. Chemicals in the blood. Yeah, absolutely. And the balance thereof. Yep. So in terms of blood pressure, obviously when you've got a change in pressure, you will have that change in red blood cell percentages, and you will have a change in the relative percentages of the chemicals in your blood as well. Okay, and the other one for the short-term regulator is the medullary ischemic response. Most of the time, you're not going to be asked for all of those. Okay, so just try and get your head around. Baro and chemo is a good place to start, right? I've got something about stretch and I've got something about composition. I've got receptors for both of those, and they're both going to send messages. And long-term, as we said, the renin-angiotensin-aldosterone system and the ANP, or the atrial natriuretic peptides. Now, one is there to lower blood pressure and one is there to raise blood pressure. Which is which, I wonder? The RAS system is there to do what? So I'll quickly look it up. Dr. Google could help you there.
Decrease blood pressure?
Yep. And the atrial natriuretic peptides are there to decrease blood pressure. Yep. So one is all about vasoconstriction and one is all about vasodilation. One is all about retaining water and salt, and another one is about pushing out water and salt. Okay, so both of these end up acting on the kidney at the end of the day, right? Making sure that we either keep stuff or lose stuff, depending on whether we've got blood pressure is too high or blood pressure is too low. All right, so that one I would suggest, guys, blood pressure regulation is kind of, I know I say this all the time about everything, but in this particular topic, it's a real meat and gravy kind of question. So I'd make sure that that one was well known and well understood. All right, let's move on. Okay, I love this question because it's my favorite trip up question. It's also a great question for you to use at like dinner parties when you want to be a real tosser and prove that you're smarter than everybody else because you studied medical science and nursing and they haven't. So if you said to a normal person, Joe average, right, define an artery and define a vein, I bet you they could, but I bet you they'd include a parameter that isn't always true. So an artery is what? Somebody?
So an artery is moving the blood away from the heart and the vein is going back toward it.
Thank you. Now, does that have anything to do with whether or not what's in it is oxygenated? Somebody else?
Well, generally it does.
Sorry, generally, yes, generally it does. Broadly speaking, most arteries are red because they have oxygenated blood and most veins are blue. But not always, because tricksy human bodies. So where is it that that's not the case?
In the pulmonary vein?
In the pulmonary circuit. Yeah, well, pulmonary vein and pulmonary artery, really, because either way, it's swapped. Yep. And that is true for the entire circuit too. So you remember that when you start looking at this week's stuff and you start talking about the veins and arteries that surround the alveolar sacs, that exactly the same thing. Yep. So the veins are bringing the blood to the alveolar sacs and the arteries are taking it back, which is interesting. Right. Okay. So it's tricky, but you just got to get your head around pulmonary circuits. Okay, there they are. So artery from vein to, usually arteries in red, blah, blah, blah. We just talked about all that. So that's just really important to remember that the pulmonary system is slightly different. Pulmonary vein, red, pulmonary artery, blue. Also very fun to, again, if you possibly can, get yourself a deceased sheep's heart or something of the kind, stick your fingers in all the different arteries and figure out which one's which coming off the heart. This will be really important, actually, if you ever get a chance to do it. I think you can get them pretty cheap, actually, from most butchers. It's a good idea. I know because you guys don't have res schools and labs anymore, but if it feel the veins and the arteries, feel the difference between the musculature, particularly in the aorta, super stretchy, super elastic, super incredibly strong, and then literally identify veins by going, which ones are the wibbly soft ones, right, that don't take much pressure at all. And then run water through the chambers of the heart and watch the passage of the water as it goes in and out. So you literally run your water into an atria, let it go down to a ventricle, and then squeeze that ventricle and see which way it shoots out down the other end. Fun for the whole family, really. You can have a dissected heart and, you know, squeeze it all over your kids. They'd love it. It's gross and they'd love it. We used to do it in labs and everyone loved it. It's good fun. All right.
So, Catherine, sorry. So this might sound a bit silly. I was just thinking about it in my head, but so like for hearts for humans and animals are the same.
Yep.
So you could do that. Like you could. Just said. Yeah.
Yeah, absolutely.
Wow.
Mammalian hearts all work the same way. So
Okay.
all you got to, well, actually, quite frankly, you could use a mouse heart too. It'd just be a bit tricky.
Oh yeah. Okay.
But you know, like a sheep's heart or a cow's heart or whatever you can get your hands on. And I really recommend this, guys, because it's a bit like blood typing. It's one understands in one's head and goes, okay, if I put the wrong antibody with the wrong blood, it will clump up, it'll agglutinate, it'll clot. But seeing it in front of you is often the aha moment. Same thing with understanding the heart. It's the, oh, cool. So if I squeeze the left ventricle, look at it shoot up out of the aorta. Sweet, that's where it's supposed to go. Yay, I knew that theoretically, and now I can see it physically happening in front of me. So I know it's gross, but I think it's worth investing in your education this way. I personally think it's worth us investing in your education this way and having res schools and things. But pros and cons, right? You don't have to travel, you don't have to have accommodation, but you also don't get to squeeze hearts. And that's always a fun thing. All right. I won't get political. That's not fair. Okay. Now, we've got questions to answer where we've got to pick one. right? So luckily, one of two answers, you've got a 50% chance of being right in any given moment. So now we've got to figure out these. All right, so either, I'm going to talk about a network here. So a portal network or a venous network is one in which blood flows through two different sets of capillaries. Now this, you could actually solve this linguistically. So normally, what do we have? Normally we've got like a venous network going through one or two sets of capillaries is a question. What do we think? Have a guess. Is it portal or venous? Someone guess. You've got a 50% chance of being right. It's better than the pokies in terms of odds. No, but good guess. Portal. Yep. So literally think of a portal being an opening to a number of different possibilities. Yep. So a portal network opens up onto different sets of capillaries. All right. The next one should be easy. This is gravy. Blood always flows from an area of something pressure to an area of something pressure. Where does it start?
Higher.
It starts at higher, yep, and goes to lower. That's the whole system of blood through the body is from an area of higher pressure to an area of lower pressure. And this makes sense, really. Think about the heart as obviously, you know, that's literally the center of the system, right? The pump. Really high pressure. And then think about the pressure in your brachial arteries, right? Where we actually take blood pressure. And then think about the pressure down your feet. Right, so obviously the smaller we get, the further away from the heart we get, the lower the pressure. Yeah. Weirdly enough, the vena cava is incredibly low pressure. So actually one of the things that is sucking all the venous blood back up is that weirdly enough, the venous vessels in your body they're not high pressure, but they're higher than the vena cava. It's really, really low pressure there. Okay, it's a sluggish, recalcitrant trickle at best. Okay. All right. The difference in pressure. So between, if I said the pressure in my calf is 12 milligrams of mercury and the pressure in my vena cava is 2 to 3 milligrams of mercury, what do we call that? The difference in pressure between one and the other.
The gradient.
The gradient. Exactly. Yeah, one number minus the other number. Yep, and that gives us that pressure gradient. Yep, good. All right. The next two should be falling off a log. When the left ventricle contracts into the aorta, we have a normal blood pressure of, and now we've got to remember our systole or our diastole as well. So what is a normal typical, well, actually, let's do the second part of the question first. Are we talking about diastole or systole when we're talking about contraction?
Systole.
Systole, good. And what is technically a normal systolic pressure then out of those two?
110.
110, absolutely. So, hey, quick question for you, for the lads and lasses in the room. Why is it that normal blood pressure is generally considered 120 over 80 when actually typical normal blood pressure for the systole is 110? Discuss.
This is just 100% a guess, but would that just be going into the individual environmental factors that goes into people, like, you know, how do I explain, like increased sodiums and things like that, or not?
Yes, absolutely. The 120 over 80 thing is a little bit like an urban legend. It just sort of becomes part of the lingo, right? So everyone goes, oh yeah, 120 over 80, that's normal blood pressure. Actually, it is not defined as normal blood pressure. So technically 110, if you're at 120, technically you're in the first stages of hypertension, which kind of means that most people over the age of, 20 are. Right? And this is one of the things we have to look at as obviously as practitioners is all right, is it climbing? If it stays there, we can put it down to, as you say, Alison, lifestyle factors and normal aging of vessels and et cetera, et cetera, et cetera. But if it climbs anywhere, we got to be really careful. It's already slightly hypertensive at 120. Yep. Just to scare you all and go, oh God, that's mine. Like, yeah, mine too. So we just have to watch it. All right. Then we have, when ventricle relaxes or diastoles, the pressure drops to an average of one of those. One of those might be yours, but one of those should be yours. Which one should be? 70. Yes. Yes. And obviously I answered the last part, diastole. Yeah. So 110 over 70. You don't have to answer this because I'm going to put up my hand and tell you what my blood pressure generally is. But is anyone here actually reading 110 over 70 on a regular basis? Oh, well done. Go Alison and her vessels. Yay. Good on you, darling. Mine sits round about 125 over 80 something, 82-ish most of the time, which ain't bad for an old fella. It's still pretty good. My doctor's okay with that. I'm not dying yet. But important for you to remember that it's still early stage hypertension, and I have to be careful with my sodium and all that. Okay. As blood moves away from the heart, blood pressure either stays the same or goes down. Which one?
Down, wouldn't it?
Absolutely. Yep, absolutely. All right. The greater the something between 2 points, the greater the flow. The greater the flow. It's going to flow faster when we have more resistance, or it's going to flow faster when we have more pressure difference.
Pressure difference.
Yeah, of course, because if we have more resistance, it's going to flow slower. That's the whole point, right? Yep. Good. Okay, a lower than, oh, come on. This should be just a chorus now. A lower than normal blood pressure is called? Chorus.
Hypertension.
Yeah, be very specific because it sounds the same. Hypo, yes, absolutely, hypo. And normal is higher than normal. The other one. Yeah, hyper. Just, yeah, you will find yourself being quite persnickety about the pronunciation of this. Who's been to a playground and like watched kids going mental and heard some mother saying, oh, don't worry about him, he's just having a hyper. Oh, sorry, a hypo. He's having a hypo. Oh my God, Cheryl, he's having a hypo. And every single medical professional should go, no, hyper, actually. But you don't want to be that particular person at a playground because you're going to get mugged or something. So yeah, you'll become very hypo and very hyper about things. All right, blood pressure. Oh, here we go. Let's identify some parameters. Blood pressure of 128 over 84. Is it normal or is it pre-hypertension?
Pre-hypertension.
It is. Guess what? That's me right there. Okay, what about 152 over 91?
Stage 2 hypertension.
Oh, yes, absolutely. Yeah, that would be alarm bells. Good. Okay. The opposition to flow that results from friction moving against the blood walls is called?
Peripheral resistance.
Peripheral resistance, absolutely. High blood pressure can come from many, many different things. That's a blanket umbrella term. What we're talking about when we're talking about friction against the walls, definitely peripheral resistance. Good, guys. All right. How did everybody go with that? Was that scary or was it okay?
It was a lot better than I thought it would be.
Okay. Well, half the point of the tutorial is to point you to the bits where you were uncertain, so you know what you can highlight in your study notes. I got to go back and do that bit. Yep. All right. Okay. Oh, there's all your answers. Okay. We just did the answers, though. You don't need the answers. Okay. This is a doozy. Ooh. Describe the action potential of your cardiac muscle cells. Now, being a describe question, it's going to be a little bit long-winded and a bit detailed. But this is something you actually do need to understand completely, the action potential of the cardiac muscle cells. What sets them off? What moves where? Which ions are moving in and out and when? And how does that actually affect the heartbeat itself? So the action potential of cardiac muscle cells. Let's start from the beginning. What sets off the action potential of cardiac muscle cells? Hint, first slide.
The SA node.
The SA node, good. And what is unique about the SA node regarding action potentials?
Because it's the first one that then creates the other action potentials to go off. So as it creating one and then creates the others to follow with lead.
Yeah, absolutely. And does it get a signal from anywhere, the sinoatrial node?
No.
No. So it's
no.
yeah. So one of the great things about this cardiac muscle and the action potential here is from the sinoatrial node, we have what we call autorhythmicity, right? It just goes, which is magical and wonderful, right? It does its thing. It just keeps on firing action potentials. Clever little thing, actually. All right. Once it has done that, though, how do our cardiac muscle cells react? What goes on with that action potential? So first of all, someone tell me, from the sinoatrial node, where does it go next?
Does it go to the other one?
Yep. The atrioventricular node, exactly. And then there's a little bit of a pause because we actually don't want atria and ventricles contracting at the same time. That would be unfortunate. Yep. Big problem with pressure. Huge. So we have to have a little bit of a pause. And then it goes from the atrioventricular node down the middle of the heart, which is, there's a structure in between the two ventricles called something.
Bundles of something.
Bundles of something. Yep, we're going to get to the bundles of something. But before we do that, we've got bundle branches, left and right. So one's going to hit the right-hand side of the heart, one's going to hit the left. And both of those travel down the atrioventricular septum, which is just a word that means divide. Yep, so it's in this divide in the middle. And then from there into the bundles of something. The bundles of what?
His,
yes. And from the bundles of his, again, like trees, we've got a few more things popping out the end of the bundles of his known as?
The Purkinje fibers.
The Purkinje fibers, good. And they're the ones that actually stimulate the cardiac muscle cells. Yep, that's our little pathway. Good. Then what happens at a cellular level? What ions go in to depolarize the cell? What ions go out?
Do sodium, the Na, go in?
Absolutely. Yes, they do. And another one that's also very important. So sodium, that's
Calcium?
one of the positive. Calcium.
Yeah.
Calcium's the huge player. Okay, so sodium in the cardiac muscle cells, the sodium channels are always open. So it kind of flows in and out depending on concentration. The calcium channels are the ones that are voltage gated. So they're the ones that really, really go and make it happen. Yep. And like other electrical cells, which is the one that buggers off and leaves the cell? This is the same as neurons. Potassium. Yeah, exactly. So really the only thing you need to remember about the cardiac action potential that's different is that it involves a lot more of those calcium channels. It's a much bigger player down here. Good. All right. Let's have a look at my little answer slide and see if I've missed anything. It's entirely possible. No, not particularly. So we have got sodium, calcium on the left-hand side there for depolarization. And then we've got our potassium doing its thing, absolutely. And then we've got, as I said, the calcium channels closing. And again, so that both the sodium and the potassium channels in the heart are a little bit leaky. So it really is calcium that's the major player. Yep, the movement of calcium is really what makes the big difference. The sodium and the potassium will move according to, apart from anything else, blood concentrations. So if you, for instance, we're talking about healthy hearts before, if you have massive sodium concentrations in your blood, one of the normal outcomes of that is that your heart beats faster. It's got more stimulation to depolarize. Yep, you may need to say this to a patient someday when they say, what's got salt got to do with my heart? It's like, well, actually it overstimulates because you've got channels in your heart that sodium likes to flow through. And, you know, anything that's going to diffuse through an open channel is going to go from an area of higher concentration to an area of lower concentration. If you've got a lot of sodium in your blood, it's going to make your heart work harder. Right? You're going to keep on getting much more depolarization and stimulation. Just made that up. Stimulation actually is the word I was looking for. All right, good. I think you've got that. We did all the Purkinje fibers and you just need to remember those 3 ions in particular. Is that okay with everybody? It's pretty much the same as a neuron. It's not that different. Yep. Just we have to think about, you know, the autorhythmicity of the sinoatrial node, the resting point at the atrioventricular, and then remembering the actual pathway of those electrical fibers as well. So you know the circuit. Okay, going great guns. All right. Now, explaining the baroreflex, I think I might have jumped the gun a bit. I made you do this a bit earlier. But now you have to really properly explain it. Mr. Baroreflex. So does anybody want to, again, I love to do this, explain it to me like I don't know nothing and I am young, which I'm not. Often don't know nothing though, that is true, particularly this time of night. When it gets towards 9, I know nothing at all. Okay, baroreflex, someone tell me what it's for. Someone who didn't tell me earlier.
Didn't you say it's got something to do with stretching and pressure?
It does. It does. That's a great place to start us off. It does, Beck. Good. Yes, stretching and pressure. And it's a reflex, which means what precisely? Does a reflex get controlled by higher brain centers or does a reflex do something else?
Isn't it?
So it's right. Oh yeah, sorry.
That's okay, but you both go, but maybe one at a time.
You go first.
From what I understand, so you mean like when you stand up and your brain tells your vessels to constrict to give you a higher blood pressure so that you don't faint, essentially.
Yeah. So a reflex is something you cannot control. It's beyond your conscious control. Yep, that's the big thing. So a reflex can be like brain to organ, and it can also be just something at synapses in the spinal cord, like your patellar reflex. Your brain doesn't even know you got hit by a hammer until well after your body has responded. Yep. So it's not under your conscious control is the main thing about the reflex side of things. Baro, stretch, and pressure. Yep, we know that bit at least. Can anyone tell me anything else about the baroreflex? So we know it's got where are the receptors that actually tell us about this problem with pressure? If we've got a problem, where are the receptors that send the message?
Receptors tell the medulla what's happening, don't they?
They do. Yeah. So where are those receptors located in the body is the question.
In the brain.
Nope.
I don't know how to say it. Carotid sinus.
Yes.
And aortic arch.
That's right. Okay. So the aorta is literally not just a pipe, but also has a ton of receptors in it. Right. And these are the baroreceptors. And as you say, they're also in the carotid sinus as well. The carotid artery is the one that leads up to your brain. Pretty important fella. So basically, 2 places, and as you can imagine, for keeping meat suits alive, the heart receptors, really, really important for monitoring systemic circulation. Of course, there's going to be receptors in the carotid because without this thing ticking on, we're zombies. Yep. So any change of blood pressure to the brain is super important. So the carotid's got some as well. Yep. We don't have enough blood coming to the brain. Super emergency. Medulla, fix that. Yep. Okay, let's have a look. All right. So as you say, the carotid sinus and the aortic arch, this is literally your lecture note. So this is what you do need to understand. Okay, detecting changes in wall stretch, and this literally has an effect on the frequency of your impulses, going from those receptors to the cardiovascular center in the brain, which, as somebody's already identified, was the medulla. Yep. Through efferent fibers in the glossopharyngeal and vagus nerves. Now, if you can remember the names of the nerves, there's a nerve now. If you can remember the glossopharyngeal and vagus nerves, excellent. If you can't, as long as you can tell me that about the fact that the signal's going to go through sensory nerves and that it's going to come back out through motor. And if you want to use the afferent terminology there, that would be good too. But, you know, just for a challenge, let's remember which one's which and see if we can figure out where the message is coming in and where the message is going out. But it's up to you. You don't have to remember those names. It's just helpful sometimes. Okay, let's move. Baroreflex. You don't need to know tons about it. Now, this one says cut these out during class. No, we're not going to sit here and watch everyone play with scissors. That's not going to happen. What we might do is just do a couple and then you can cut things out later and play with them for yourselves. So let's see if we can play matchy-matchies. So stroke volume. Is that right? Did I match it up correct? Lee? Is that measured in mils per beat? And is it the amount of blood that comes out of a ventricle, do you think? Yes, Diane thinks I'm right. That's good.
I remember reading it somewhere.
That's comforting. No, it's good. It's good. I'm glad. I'm glad I got that right. That's excellent. Okay. What about, is heart rate correct? Have I got that definition right there? Everyone should be frantically nodding right now because one of the first things you'll do with any patient is take their heart rate per minute, right? Beats per minute. What is the ideal heart rate? Lads and lasses, what do we want to see in most people? Resting heart rate.
Is it like 65 or something?
Yep. And lower if you happen to be a Buddhist monk. Or an extremely, extremely fit person. So mine's around about 70 most of the time, which is not awesome. I should try and get it down by doing more exercise, but I'm too busy teaching and I do a lot of that sitting, unfortunately. Okay, you can do this exercise yourselves. Match the term with the definition. Right? This is not kindergarten. I don't need to do that for you. All right. Now, last and not least, where are we on time? How am I doing? Killing it. Fantastic. All right. So I named this, I decided to give it a romantic title so that we could jump out of tutorial land and imagine a story. So this is called Jake and the Troubled Heart. It's very Mills and Boon, as you can imagine. So is the name, actually, Jake. It's a very manly kind of name. All right. Imagine Jake as you will. Right. He's probably got, lots of square stuff going on here and lots of bumps down here. I mean, the chest ones, guys, don't be gross. All right. So Jake, Hot Jake, has been admitted to hospital to receive a pace. Oh, that's a shame for poor Hot Jake. His heart rate had become so slow it was giving him discomfort. An ECG shows there's a problem with his electrical system, not how much he feels. He still feels everything, Jake, because he's in my book. So, and he's hot, right? So he's a feeler, but his electrics aren't working out so well. Describe the electrical system of the heart, and it says research, but I don't want you to do a whole ton of research right now. I think we're going to imagine instead why this might be a problem. So describing the electrical system of the heart, and if you want to, you can characterize and you can explain the electrical system of the heart to Jake in a low, comforting murmur. Or you could just tell me, I don't mind. I'm just trying to make fairly dry material reasonably fun. Okay, so there's a problem with his electrical system. what do you think, if his heart rate has become so slow, what can we deduce from that? What can you?
That is,
Sorry.
that his SA node, his SA node isn't firing often enough.
Yes, absolutely. So we already know that. Yep. Okay. And of course, that's going to, the atrioventricular node can take over to an extent, but not completely. All right. So if one's gone, the other one's affected as well, generally. Okay. So poor old hot Jake has a problem with his SA node. That's a bit of a problem. We'd like to keep him alive because he's hot. We don't really want hot people dying. It's not right. So what is a pacemaker, and why are we going to put one in Jake? What does a pacemaker do? Someone have a quick look up what they can find in terms of pacemakers.
It will regulate the heart rate.
Yep.
Yeah.
Yep. Artificial regulation of the heart rate. Literally popping a little machine in there to generate those action potentials instead. Yep. So that is exactly why a pacemaker would help Jake. Very good. So this is not a complicated question, actually. I just made it way more complicated than it needed to be because there was abs and there was hair and there was a whole character. Really wasn't part of the clinical diagnosis, though, was it? It just would be a pleasant patient to have, really. You know, it's always nice. Not to be shallow, but I am a little bit sometimes. Okay, so here is a whole whack of info for you on pacemakers. Okay, so literally, we already know about the conduction system. We talked about that before, which is good. And literally, it's an artificial electrical impulse providing that discharge that maintains the ideal regular heartbeat. Okay, so there's a whole bunch of different ones, but again, sometimes it's a matter of replacing the sinoatrial node itself and everything else is fine. Sometimes it's a matter of replacing the whole system. Okay, fibers, etc. Right, so there's a whole bunch of ones that actually have, different leads that go all over the place to your right and your left ventricles and make sure that everything's working out. So it can be a relatively simple operation. It can be very, very complicated depending on the level of sinoatrial dysfunction. So that's something fun for you to look up this evening and have a look at the different kinds of pacemakers, different kinds of outcomes, who's generally diagnosed with what and what do we tend to do about it. Not part of your course, not part of the things you're going to be examined on, but fun, and definitely something I'd like you to try and do to just cement that understanding of the electrical conduction system of the heart. Yeah, it's always good to have an application for the knowledge, not just theoretical, but so what does happen? Like what do we put in them and how does that work? Yeah, cool. All right. I believe that brings us to the coda of the tutorial. It does. Are there any worries, questions, thoughts about whether Jake is blonde or dark? How many abs can you actually see? I mean, you're going to have to take his shirt off, right? So is it a 6-pack? Is it an 8-pack? Should we just reach for the stars and go for the 8? Right? Is he that ripped? I think we should, right? Yeah. Okay. Does Jake have a partner? You're going to have to explain it to her. How will you do that? Are you jealous? Are you going to stick her with something when she's not looking? I probably would. Anywho, I will let you go. Enough about Jake and the troubled heart. Any thoughts or questions, guys? Apart from Kath, you're insane. Get off.
I don't think there's many Jakes in a cardiac ward, to be honest.
No, I don't think so. Not often. Although it has happened. One of the fittest guys I have ever known, like jog every day, gym every day, vegan, literally vitamin supplements, blah, 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 dead at 34, heart attack. Went running and just went, boom, dead, 34. And all the stuff we've been talking about. So yeah, can happen. They don't often end up in a cardiac ward though, you're right, because usually it's not degenerative, it's not slow, it's just quick. If it's going to go, boom, you're gone. All right, go have some dinner. Yeah. Oh my God. Yeah, Maddie. So yeah, it's not just my anecdote, but yeah, it does happen. Young and healthy and handsome and goodbye. Life is short, so enjoy it. I will see you guys next week for so much discussion about itty tiny bitty vessels and how they wrap around stuff and how we exchange stuff between them. Are they fenestrated? Are they not? Stay tuned. It'll be so exciting. All right. I'll see you guys next week. Thanks for coming. See you guys.